You've probably heard that AI is expensive to train and run, but have you ever wondered why? Why can't you just run ChatGPT on your laptop the same way you run a spreadsheet? What's actually happening inside the computers that power AI? And why are those computers worth tens of thousands of dollars each? The answer comes down to hardware, the chips, the specialized processors that make modern AI possible. And right now, there is a full-blown geopolitical and industrial war being fought over who controls these chips. The outcome will determine who leads in AI for the next decade. Let me break it all down. To understand why AI needs special hardware, you have to understand what AI actually does computationally. At its core, training and running an AI model comes down to an enormous number of matrix multiplications. Matrices are grids of numbers. Multiplying them involves taking rows and columns and doing thousands of addition and multiplication operations to produce a result. For a neural network, this happens billions or trillions of times per second during both training and inference. A traditional CPU, the main processor in your laptop or desktop, is designed to be a generalist. It has a relatively small number of very powerful cores, usually 4 to 16 for consumer hardware, designed to handle complex, varied tasks in sequence. It's great at running your web browser, managing files, executing diverse code, but it's not optimized to do billions of identical simple math operations simultaneously. A GPU, graphics processing unit, was originally designed for rendering graphics. Rendering a 3D game requires computing the color and position of millions of pixels simultaneously, which means doing massive amounts of parallel math. GPUs have thousands of smaller, simpler cores designed to work in parallel. NVIDIA's H100, their flagship AI GPU, has over 16,000 CUDA cores. That parallel architecture turns out to be exactly what AI needs. The shift from CPU to GPU for AI training was one of the most important inflection points in the history of deep learning. When researchers started training neural networks on GPUs around 2010 to 2012, training times dropped from weeks to days. That speed up unlocked the entire deep learning revolution. It would be impossible to discuss AI hardware without talking at length about NVIDIA. They are not just the leading company in AI chips. They are, at this moment, arguably the most important single company in the entire AI industry. NVIDIA makes the GPUs that power nearly all frontier AI training. The H100, the A100 before it, the upcoming B100 and GB200 Blackwell architecture. These chips are so in demand that there are waitlists measured in months. When Sam Altman, CEO of OpenAI, flew around the world trying to raise money to build AI chip manufacturing capacity, it was in direct response to how bottlenecked the industry is on NVIDIA hardware. How did NVIDIA get here? It wasn't just hardware. In 2007, NVIDIA launched CUDA, Compute Unified Device Architecture, a programming platform and ecosystem that let researchers use GPU power for general-purpose computing. CUDA became the standard. All the major AI frameworks, TensorFlow, PyTorch, are built on top of it. Billions of dollars in AI software tools, research code, and infrastructure are designed around CUDA. This creates an almost insurmountable moat. Even if a competitor builds hardware that's technically better on paper, the switching cost is enormous. Companies would have to rewrite massive amounts of code, retrain their engineers, and rebuild their entire infrastructure stack. NVIDIA's software ecosystem is as much their competitive advantage as their silicon. Their 2024 revenue and market cap trajectory reflected this. NVIDIA briefly became the most valuable company in the world during the height of the AI chip boom. NVIDIA's dominance doesn't mean no one is trying to compete. AMD is the most obvious challenger. Their MI300X GPU has gotten serious traction, particularly because it has significantly more memory bandwidth than the NVIDIA H100, important for running inference on very large models. Microsoft, Meta, and other hyperscalers have been running workloads on AMD hardware to diversify away from NVIDIA dependency. AMD is real competition, but they remain well behind NVIDIA in software ecosystem maturity. Intel has attempted multiple times to break into the AI accelerator market. Their Gaudi chips have had limited success, and Intel's broader business struggles have made their AI push inconsistent. They're not out, but they're not a leading player right now. Startups. A wave of AI chip startups has emerged, each with a different architectural bet on how to best accelerate AI workloads. Grok offers extremely fast inference, not training, by using a deterministic architecture that avoids many of the bottlenecks in traditional GPUs. Cerebras built a chip the size of a wafer with over 900,000 cores. Sambanova, GraphCore, and others have all brought novel approaches. Most of these are finding niche applications rather than displacing NVIDIA broadly. Beyond the commercial chip market, the big tech companies are building their own custom AI chips. Google's TPUs, tensor processing units, are the most mature example. Google designed them specifically for machine learning workloads and has been using them internally to train their models for years. The latest TPU v5 is an extremely capable chip that Google uses for Gemini training and inference. Google also offers TPU access through Google Cloud. Amazon AWS has Trainium chips for training and Inferentia chips for inference. Microsoft has been developing custom AI silicon. Apple's Neural Engine, built into every Apple silicon chip, is a smaller scale but highly efficient AI accelerator. The trend among hyperscalers is clear. Rather than being entirely dependent on NVIDIA, they want custom silicon they control. The economics are compelling. At the scale Google or Amazon operates, even a 20% efficiency improvement on custom hardware translates to hundreds of millions of dollars saved annually. Here's where things get geopolitically intense. AI chips are now considered strategic national security assets by the United States government. Beginning in 2022 and tightening significantly through 2023 and 2024, the U.S. government has imposed sweeping export controls on advanced AI chips destined for China. The restrictions cover NVIDIA's H100, A100, and even certain lower-tier chips, essentially any chip above a certain performance threshold for AI workloads. The goal is to slow China's ability to develop frontier AI. The concern at the national security level is that advanced AI could be used for surveillance, autonomous weapon systems, cyber attacks, and a range of other military and intelligence applications. Allowing China unfettered access to the best AI accelerators is seen as a threat to U.S. technological and military advantage. China's response has been to pour enormous resources into domestic chip development. Huawei's Ascend chips, while still behind NVIDIA's best, have been improving and are being used extensively within China. SEMIC, China's leading conductor manufacturer, has been pushing the limits of what's achievable without access to the most advanced Western equipment. This dynamic, the U.S. trying to maintain a chip lead while China races to close the gap, is one of the defining geopolitical competitions of our era, and it's playing out in server farms, boardrooms, and government offices simultaneously. The hardware roadmap for AI is as ambitious as it's ever been. NVIDIA's Blackwell architecture, GB200 and its variants, promises dramatically higher performance and memory bandwidth than the H100. Their NVLink interconnect technology allows multiple GPUs to share memory as a single giant system, enabling models too large to fit on any single chip. The industry is also exploring entirely new computing paradigms for AI. Photonic computing, using light instead of electrons, offers the potential for dramatically lower power consumption. Neuromorphic chips modeled on the human brain are being researched at Intel and elsewhere. In-memory computing architectures aim to eliminate the bottleneck of constantly moving data between memory and processor. The energy consumption question is also becoming urgent. Large AI training runs consume megawatts of power. Data centers for AI inference are projected to consume a significant fraction of global electricity generation within a few years. This is driving investment in more energy-efficient architectures and nuclear energy partnerships from companies like Microsoft and Google. The story of AI hardware is a story about who controls the most important technology of our generation. Right now, that means NVIDIA's chips, Taiwan's TSMC foundries, which manufacture most of the world's advanced chips, and an ongoing geopolitical battle that's reshaping global supply chains and national security strategies. Understanding this layer, the physical hardware underneath all the impressive AI capabilities you use every day, gives you a much clearer picture of where AI's real constraints and real opportunities lie. Like and subscribe if you want to keep understanding the infrastructure behind the technology that's reshaping our world. New video every week. See you next time.